Alright, first night sky news of 2020, and we clearly have to talk about Betelgeuse. Because, well, you've all been asking me for about a month to talk about Betelgeuse, and we had to wait till now to do it. Seriously, the night sky news I did in December was pretty much one of the last things that I did before I finished for Christmas break. And when I posted it, I was like, God, I really hope nothing happens in the intervening month that's like super major in the sky. Well, it didn't go supernova at least, but it did give us a little bit of entertainment over the Christmas break anyway. So we'll get to that in the news portion of this video, but first up, let's start by looking up to what we can see in the night sky in the coming weeks. Alright, at the end of the month, on the 27th, 28th of January, look southwest after sunset, so basically in the sort of general direction that the sun sets for you, and you should be able to see Venus incredibly bright in the night sky. Like, it's the brightest thing in the night sky, so if you've seen something that bright, it's probably Venus. And then the crescent moon is going to be really close to it at that time too, so you can definitely be sure that what you're seeing is Venus. On the 27th, it'll just be below Venus, and then if you look at the same time the next night on the 28th, you'll see that it's moved above Venus. Now that's a good thing to try and spot if you're a beginner. If you are a little bit more advanced, then I would also suggest trying to find Neptune at the same time, because it's going to be very close to Venus in the same part of the sky. So Venus is a good sort of jumping off board to then find Neptune, but you will need a telescope to be able to spot it. You're not going to be able to do that naked eye, binoculars, camera phone, whatever. So if you don't have a telescope and you want a chance at seeing Neptune, maybe look up, see whether there is any astronomical societies in your area that have all that kit already. You can go along to one of their meetings and see if you can spot it. Similarly, in the first half of February, at least for Northern Hemisphere observers, we're also going to be able to see Mercury in the same part of the sky, but it will be very low on the horizon as it starts to rise for us. If you're in the Southern Hemisphere, you're actually going to have to wait till sort of September time to see Mercury in the night sky. But my fellow Northern Hemispherians, you should definitely keep a lookout. It will be very low on the horizon, so quite difficult to spot, but always very proud of myself when I do find Mercury. The beginning of February is also a great time to try and look for the winter hexagon in the sky, especially because the full moon in February at the beginning of the month is going to be smack bang in the middle of it. So the 6 stars in the winter hexagon, the winter circle, whatever you want to call it, will literally ring the moon. So find Orion, or find the moon since it is going to be there. But if you find Orion and then head sort of like down and left to Sirius, at least down and left if you're in the Northern Hemisphere anyway. So starting from Sirius, head up until you see the next brightest star, which will be Procyon. Then head over to Pollux, which is part of Pollux and Castor in the Twins, Gemini constellation. Then go over to Capella, down to Aldebaran, the very red star that's sort of the eye of the bull in Taurus. Then head back down to Rigel, which I like to think as Orion's sort of foot, which again is a very, very bright blue star, and then you can finish the hexagon by connecting Rigel back up to Sirius again. As it happens, Betelgeuse is also pretty much back smack in the middle of the winter hexagon as well, but we'll get to that. By the 10th of February, I think Mercury is going to have risen enough so that I think pretty much everyone's going to have a chance of spotting the 5 major planets, so Mercury, Venus, Mars, Jupiter, Saturn, in the night sky on the same day. So Mercury and Venus, like I said, southwest, just after sunset, have a look for those 2. Then on the same day or the next morning, look about an hour before sunrise for Mars, Jupiter, and Saturn. So Jupiter especially will be easier to find. Mars probably as well, Saturn less so, but if you can look along the ecliptic, which is the sort of line the sun takes in the sky and all the other planets, because, well, the solar system is all on one plane, then you can sort of use that sort of imaginary line connecting all of them to try and find Saturn. Obviously, another thing to look for in the sky right now is Betelgeuse, because it's a lot fainter than it normally is. So I guess I could have put this section in here, but it's more news, so let's just not waste any more time and just get straight into it. So since October, Betelgeuse has been dimming. It's been getting fainter. Now that's not unusual. Betelgeuse is a variable star, so its brightness changes all the time. In fact, its brightness changes on a period of about 100 to 180 days or so. Then it also has like a secondary period as well over sort of like 4 or 5 years. So Betelgeuse changing in brightness, not a big deal. Why then, at the end of December, did it become such a big deal all of a sudden and there was all this hype in the media? It's because it reached a historic low. Proper records began sort of at the beginning of the 20th century. And since then, this is the lowest in brightness that Betelgeuse has ever been. What's amazing though is that this drop in brightness, yes, it's a historic low, but also it took it from being like one of the top 11, because it wasn't ever in the top 10, but the top 11 brightest stars in the night sky to being the 21st brightest star in the night sky. So that if you go out and find Betelgeuse, sort of the shoulder of the Orion constellation, like just above the belt, then it is noticeably fainter. It used to be about the same brightness as Rigel, sort of the foot of Orion on the opposite side of the constellation. But if you look at them both now and compare them, you can see that it is nowhere near the same brightness as Rigel anymore. And the reason that Betelgeuse is variable is because it's not what we call a main sequence star. So it's not a star in its normal hydrogen-burning life cycle like, say, the sun is. It's passed through that and it's now swelled to a red supergiant. And what happens when you get to this stage is that it's not very stable. It's burning a lot of helium in its core and other heavier elements, and so the energy given out by those reactions fluctuates a lot. And so you can imagine this scenario where there's energy pushing outwards from the nuclear reactions, and instead of being perfectly balanced by the gravity pulling inwards, like in the sun's case, there's sort of this swap and change where sometimes gravity wins for a while and the reactions get stronger and push against the gravity pulling inwards. And so you end up with this pulsing variable star. And that's what happens when stars are close to the end of their lives. To give you some context, if the sun was the size of a tennis ball, then Betelgeuse would be the size of the London Eye. It's huge. It's a mammoth star. But even though it's so much bigger in size than the sun, in terms of mass, it's only about 10 to 20 times more massive than the sun. You could almost sort of describe it as this red hot plasma vacuum, because the distance between the particles is just so great. It's so underdense. And yes, it is ready to die. It is ready to go supernova. But when I say that it's ready or that it's close to doing so, I'm talking astronomically. You might be wondering why dimming would mean supernova, because supernovas are these massive bright explosions. In fact, if Betelgeuse did go supernova right now, you would be able to see it during the day, like you can sort of the moon when it's a half moon. You can see that despite the glare of the sun because it's bright enough. You would also be able to see Betelgeuse. Anyway, why dimming equals supernova is because supernova are triggered by the end of nuclear reactions and essentially gravity winning and crushing all of the layers of the star back in on itself to the core, where it then rebounds off this solid core outwards in this huge explosion. So the hypothesis is that it's dimming, gravity is starting to win because the nuclear reactions are slowing down, and perhaps therefore it is going to go supernova. And of course the media jumped on this, because yes, it would be so exciting if Betelgeuse went supernova, and all of us astronomers were secretly praying that it would, whilst at the same time knowing it probably isn't going to. Yet. Anyway. What we do expect is that because it started dimming in October, that's about 100 or so days ago, which is the period of sort of Betelgeuse's normal dips in brightness that we have recorded before. So in theory, Betelgeuse's brightness should start climbing again as we get into sort of February, March time and through the early parts of 2020. If that happens, then we know that this was just a random fluke and probably Betelgeuse is fine and it's probably still not going to go supernova anytime soon, at least in our lifetimes. We have tried to estimate how long Betelgeuse has actually got though, based on, the models we have for stellar evolution that sort of explain stars that we see in the sky, which aren't perfect, but they do a pretty good job. And based on all the things we know about Betelgeuse, so its mass, its size, its rotation period, its periodicity and how often it varies, how many heavy elements it's got inside of it, which we get from sort of that quantum fingerprint of light from Betelgeuse. And applying all that to the models that we know, this paper that came out in 2014, which was led by Dolan and collaborators, found an estimate of 100,000 years left in Betelgeuse's lifetime. Now, obviously that has some uncertainty on it, but it's not 100,000 years plus or minus 100,000 years, in which case we don't think that Betelgeuse is going to explode anytime soon. Having said all that, that's still our best educated guess from the current best theories we have, and it could turn out that Betelgeuse massively surprises us all, which, admittedly, I am still secretly hoping for. Okay, next up I want to talk about Proxima Centauri. So many of you might know that is the closest star to the sun, and we discovered a planet around it not that long ago, Proxima Centauri b, that made a lot of waves, which was very exciting. But what if it had two planets? Proxima Centauri c was just announced. This is a super Earth, so it's more massive than the Earth. They estimate it to be about 1.9 times the mass of the Earth, and it has about a 5-year period, so it's quite far away from its star. And crucially, its star is actually a red dwarf star, so it's nowhere near as hot as the sun. So Proxima Centauri b, which was the planet they found back in 2016, was in the habitable zone of that star, and it only had a period of 11 days. It was only something like 5% of the distance between the Earth and Sun that it was orbiting around its star Proxima Centauri, and that put it in the habitable zone. Can you imagine like an 11-day year? The seasons would last like 3 days each. That would be crazy. But Proxima Centauri c, being a lot further out from its star, needing 5 Earth years to go around, means that it's probably about minus 200 degrees C. So probably not as exciting as discovering a planet in the habitable zone around our nearest star, but still excited to know that our nearest star has like a system. It's a star system, just like the solar system. It's not just one lone star and a planet. It is at least 2, they think. They do need more observations to confirm the result that they found. So it will probably be one of the key targets to take a direct image of that star system with the James Webb Space Telescope when it launches next year? Oh, 2021, come on, James Webb Space Telescope. So I'm really excited to see whether James Webb can spot it and whether that'll confirm its existence as well. And now we turn our attention back to the crisis in cosmology, which I know a lot of you are like, it's not a crisis. The climate crisis is a crisis, yes. But it's been dubbed now, that's what it's known as, we're rolling with it. And because it's been dubbed and given a name, there seem to be this flurry of results now that are coming out with people trying to explain what might be the issue here. So for those who haven't heard about this crisis in cosmology, first of all, I did make another Night Sky News on this a couple of months ago, so if you haven't maybe seen that, maybe go watch it. But in summary, we don't really know the age of the universe very well, and we're wondering whether it's because there's something wrong in our models of sort of a universe that has 5% matter, sort of 20-ish% dark matter, and then sort of 70% dark energy, which is sort of a force that's acting opposite to gravity to cause the expansion of the universe. And we also think that it's causing accelerated expansion of the universe as well. But all these different methods of working out what rate that expansion is happening at and how old the age of the universe is, therefore, because of it, are all giving us different answers. And then back in November, people were like, oh, maybe we can fix this if we let a couple of other parameters in our model change. And when they did that, they ended up with a different shaped universe than we previously thought. And also, it kind of made everything worse as well. So basically, all of our sort of best models of the universe are a little bit up in the air because we're trying to use the observations and the data we have to construct a good model, but when all of those conflict, it's a little bit difficult. So there's a couple of different ways you might be able to attempt to fix this. The first one is to find if there is an error in the data we are using, or perhaps there's some assumption we've made that affects everything and is sort of like a cascade downwards. The other way is finding a method that is completely independent of all the other methods to see what that gives us. And that's a little bit difficult because sometimes there's some piece of knowledge that we've learned by studying this thing that uses in this method that we need for that method, and so it is kind of circular, but there are ways we can do it if we're clever about it. So there's a paper that came out right at the end of December by Kang and collaborators that took the first approach. Let's see if there's an error in our data or our assumptions somewhere that might be affecting everything. And what they looked at in particular were supernova. So supernova have been used for a long time to try and measure the expansion of the universe, because there's a specific type of supernova called a type 1a, it's not a very inventive name, I know, that always explodes with the exact same brightness. And we know that's the exact same brightness because physics tells us it is that way. What's happening is that there is what's called a white dwarf star, which is held up by the pressure of trying to push electrons together, and they're repelling each other. And it's literally sort of like the densest way you can pack sort of atoms with free electrons, at least, around them. And that's orbiting another star. And because that is very, very dense, it's dragging off a lot of the material from the other star. And slowly it builds up its mass and builds up its mass, and gravity pushing inwards on the little white dwarf star is getting stronger and trying to crush those electrons together more. Now, eventually, you reach a point where gravity is strong enough to overcome that force of electrons repelling each other. When that happens, it goes supernova. Now, we know the charge on an electron very well. It's been measured many times. So we can work out the force that there would be between two of those electrons repelling each other. You would then know how much gravitational force you would need to overcome that and force them together. So you can work out how massive the star would have to be in order for it to essentially crush itself. And because the charge doesn't change, then the force that you would need from gravity doesn't change, and therefore the mass doesn't change. And then because of E equals mc squared, the energy and therefore the brightness you get out doesn't change. And so that is an assumption that has underpinned every supernova study. Because if it doesn't change, then wherever you observe it in the universe, then you can work out how far away it is because of how bright it appears compared to how bright you know it should be. So then you have a distance to, say, a galaxy that's billions of light years away because a supernova went off in it, a type 1a supernova. You can then measure the redshift of that galaxy, i.e. how fast it's moving away from you because of the expansion of space. And if you do that lots and lots and lots of times, you essentially get the rate that the expansion is happening at with distance, and therefore you can see if it's accelerating, expanding, i.e. the larger the distance you get to, the more the universe is expanded than you would have thought. Now that work showing that with supernova won the Nobel Prize about a decade ago. And rightly so as well. It was a major discovery showing that the universe wasn't just expanding, it was accelerating in its expansion. Now this work led by Kang at the end of December questioned that basic assumption, that it should always go off at the same brightness. Because some models have shown that if the white dwarf star wasn't just pure helium atoms, if it had some trace heavier elements in there like carbon or oxygen or nitrogen, something like that, then that could actually affect the repelling forces between electrons, disrupt it, and so it would actually explode at a slightly different mass, giving you a slightly different brightness. And that's actually really important because if we think about sort of the very early universe, stars form. The first generation of stars, they're forming from pretty much pure hydrogen. They turn a lot of it into helium. Some of them go supernova and put traces of carbon, oxygen, and nitrogen in the surrounding area. A new generation of stars forms from that material. Then it's not forming from pure hydrogen. It starts with something that's already got a couple of traces of those elements in, does the same thing again, puts more of those elements into the surrounding area. Now that's great for the solar system because by the time the sun formed, there was enough of that stuff to make the Earth and you and me. But it means that when you then form a white dwarf, which is probably what the sun's going to end up as, you're going to have a lot more trace elements in there than you did, say, a white dwarf that was formed at the very beginning of the universe, say, a billion years after the universe formed, rather than 13 billion years after the universe formed. So what Kang was looking at was whether the brightness of a supernova changes with, say, the mass of the galaxy that it's in, or the star formation rate of a galaxy that's in, or maybe even just the shape of the galaxy, because the shape of the galaxy sort of traces how many mergers it's had in its history, and mergers bring in fresh gas, and maybe that could be contaminated by more and more metals, or maybe it's purer gas. It all depends. So from the apparent brightness that we observe at greater distances, we might actually infer that it's closer to us than it actually is. Which means that that piece of evidence we have of that accelerated expansion of the universe that won the Nobel Prize actually the ones at greater distance might be further away than we originally thought, and that could actually be a straight line, and it's just that the universe is expanding but not accelerating expanding, and that dark energy might not be as big of a component of the universe as we first thought. Maybe? But there is so much other evidence from other different methods that don't actually rely on the supernova that show that dark energy still does exist. So it's very confusing. Like, just 6 months ago, there was a paper led by Wang and collaborators that looked at the second option I said. Look for an independent method that doesn't rely on the supernova or the cosmic microwave background, which is another very oft-used method to look at this thing. And instead, they actually looked at the lensing of galaxies, so background galaxies by big clusters of galaxies in the foreground. And they ended up finding evidence for dark energy that was pretty much the same amount as suggested by supernova before you do all these corrections due to the age of the population. This is a little difficult to wrap up now, but essentially, everything contradicts everything at the minute, which is a good thing. Because if everything was fine, we wouldn't be learning more. And that's what science is all about, learning what we can when nothing makes sense. Crucially, I think what all these results are telling us is that our current best model, that one of sort of 5% matter and 20% dark matter and 70% dark energy in an accelerating, expanding universe, might just be a little bit too simple to explain what we're seeing. And we actually need another layer of complexity that we haven't wrapped our heads around yet. Which we shouldn't be surprised about. The universe doesn't exist so that we can understand it, right? It would be arrogant of us to assume that the grand theory to explain the entire universe should be understood easily by us humans and should be a nice, simple theory that we can package up with a bow. Because the results are showing us, the observations we make are showing us that is not the case at all. But we can sure as hell try. Just before we get to the bloopers, I want to tell you about an exciting new podcast that I've gotten involved with. It is the Royal Astronomical Society's 200th anniversary year. And to celebrate this, they're doing a podcast every month on a whole host of different topics. I am the co-host of this podcast, and we're recording one each month in the Royal Astronomical Society Council Room, which, let me tell you, is incredible. This month's podcast is already out, and you can hear it wherever you find podcasts, but I will put the links in the description below as well. This month's theme was black holes and dark matter, the unseen, if you will, which obviously I love talking about. I even got to touch a second edition copy of Copernicus's book as well, which I still haven't quite wrapped my head around being able to do, but I did. And I hope that you will all enjoy it, at least getting to hear me through proper, nice radio quality microphones as well, rather than this piddly little thing which I have at home. So if you're up for that, go check it out. The RAS's podcast is called Nevermind the Space Rocks. I've started recording and I haven't got my mic plugged in yet because this. Thanks, past me. Chaos theory at work. Like, ugh. When will I learn? It's like everyone always says, physicists, they must know all the laws of nature and the world, and therefore none of this kind of stuff must ever happen to them. Well, you know what? We're also lazy and busy, and so we end up in this horrendous situation. Ta-da! It's a really good feeling to have a 4-meter cable untangled. Oh, stupid flimsy top. It'll do. Clearly that top did not do because I went and changed it. From Sirius, you're going to go up to Procyon and then Pollux in the Gemini constellation, the twins, and then over to, why do I always forget Capella's name? Pollux Capella. But a paper that came out in 2014 tried to put a number on how long Betelgeuse had left to live. It was led by Dolan and collaborators, which I've just realised makes it sound like the Dolan twins wrote it. Oh, I'd love that. They're taking a break from YouTube and they wrote an astrophysics paper. Toss a coin to your witcher, oh valley of plenty, oh valley of plenty. There's a crisis in cosmology. Doesn't fit. Don't make it. Don't try and make it fit. There's a crisis in... Toss a coin to the crisis, oh in cosmology, oh in cosmology.